what we did last time. I had given some example values for these heats of formation, made a mistake. There's not supposed to be a decimal place, that's supposed to be a comma. That means you're off by about 3 orders magnitude in what we said as last time. Okay, so we were talking about this equation that's used to find the adiabatic flame temperature, and the point I was trying to make there is if you want to have a fairly high adiabatic flame temperature for the products which is given by having this Ni double prime over here, then what's given to us is Ni single prime and T1 and maybe the pressure that's given to us which will determine Ni double prime in a way that we will see, okay. But effectively what's happening is if you now have a T1, let us suppose that is significantly low, could be 298 Kelvin or maybe 500 Kelvin or 700 Kelvin, but it's not supposed to be, it's not expected normally to be something like the adiabatic flame temperature itself. So effectively the sensible enthalpy of the fuel is going to be low because the temperature is, the initial temperature is low, okay. If you want to now have a high value for this, that means you want to have a high sensible enthalpy for the products, that means we want to have a high negative value of the heats of formation, standard heats of formation for the products, okay. So those are the ones that actually give you stable products. You get stable products mainly when the products are having high negative heats of formation, yeah, and then this total will be such that you get a fairly high sensible enthalpy for the products and therefore the adiabatic flame temperature. But if the total itself has to be high, then given that the sensible enthalpy of the reactants is low, and let us say that one of the reactants is oxygen, which is like a reference element, therefore the heat of formation, standard heat of formation for that is 0. We are looking for this total to be high only by looking at the heat of formation, the standard heat of formation of the fuel, okay. That means we want to have the standard heat of formation of the fuel to be high, okay, or in other words you look for a substance which has a high standard heat of formation, then you can identify that as a fuel. That's how we basically look at it, right. So if you look at typical values of the heats of formation, standard heats of formation for typical fuels, let us say I have listed here taking the source from S.R. Tern's book. Let us say we have methane, acetylene, ethene and ethane and propene and propane, right. So you can keep on going to higher and higher hydrocarbons. We see that some of them are negative, some of them are positive, okay, but what we are looking for is essentially that even if they are negative, they should not be high negative values, okay. So it could be somewhere around 0, negative or positive. Positive is better, but we don't want them to be as high negative values as the product standard heats of formation, so that we will get some high temperatures there, okay. So this is how you are essentially looking for identifying the fuel. This is one point that I wanted to make. The second point I wanted to make today is by actually looking at it this way, we are constructing a hypothetical set of reactions that don't exist in reality, but it's actually somewhat in our minds for a thermodynamic convenience, because thermodynamics we are dealing with enthalpies here. We recognize that these heats are all enthalpies and these are state variables, right. So it's sufficient for us to actually go from one state to the other, okay. So the way we are doing this in decomposing the enthalpy of the reactants into the standard heat of formation and the sensible enthalpy, and we are also decomposing the enthalpy of the products into their standard heats of formation and their sensible enthalpies. That is what we have done, right. So what is essentially going on is you are starting with a set of reactants which are at some temperature and pressure, okay. So by virtue of being at some temperature, they are having a certain sensible enthalpy which is non-zero, okay. By looking at this kind of thing, what we are doing is we are now bringing the reactants from their given initial temperature to the standard condition, by which let us say we now take away some heat, okay, and cool this, and we now bring it to the standard state. So we now supply the heat of formation, the standard heat of formation, to these reactants at the standard condition, alright, and go through reverse formation reactions to make the reactants unwrap their bonds and give rise to reference elements. So you now have reference elements at standard state, okay, and you now have the reaction happen, that is, you now have reference elements. These reference elements now regroup themselves to form the products at standard state, thereby releasing the standard heat of formation for the products, okay. And finally we still have in this budget, okay, we still have some heat that is available to us, which will be used to raise the sensible enthalpy of the products from the standard state to wherever it can go, so that you have heat used up all the heat that is available, okay. So the most of the heat was actually available to us in this process. When you now try to actually form the products, you got a lot of heat, okay. That heat has to simply, and then you have supplied some heat to actually unwrap the bonds of the reactants to the standard state. So you have to negate that, okay. You got some heat by getting the reactants from their initial temperature down to the standard condition. Let us suppose that the reactants were heated up to 500 K, okay. There is already some sensible enthalpy available with them, which could be taken into account when trying to bring them down hypothetically to the standard condition, right. Keep that heat with you, supply some heat for unwrapping the bonds to get the reference elements, and then get the reference elements to form the products. You get a lot of heat over here, little bit of heat over here, you have supplied some heat over there. All that stuff now will add up to some net heat that is available to you, which you now dump on the products to raise their temperature all the way to the adiabatic flame temperature, whichever temperature they can go to, okay. So it's like a circuitous path, thermodynamically speaking, that we are taking for the reactants from their state to their standard state, and then you form the reference elements from the reactants, and use the reference elements to form the products, and then raise the temperature of the products to whatever, okay. So this is the circuitous path that we are having in our minds while we are doing this, okay. Yes.
They all are fuels. So why they are heat of formation? Some have negative value and some have.
This has got to do with the way the bonds are in there, okay. So you have like some of them are saturated bonds, some of them are unsaturated, and so on. So that is something that we won't get into in this class, okay. This is like there is a thin line that is separating us from chemistry itself, okay. So we won't get into that, but the point I am trying to make is the numbers, okay. These are not supposed to be as high negative values, okay. So it's okay if they are negative values, but they shouldn't be very high negative values, okay. And if they are 0 or positive, better, okay, as high as possible. That is algebraically high is what we are looking for, okay. And the other point I wanted to make is, so in all these things we have actually said there is like a adiabatic process that is going on. That means we are not simply getting any heat at all, right. Does that make sense? When I burn stuff I get heat, huh? What are we talking about? Adiabatic. So it's not as if I am trying to say that this is an ideal thing and in reality there is some heat loss, so it is not adiabatic and all that stuff. No, in reality you are not very far away from the situation for most applications, okay. In the core of the combustion process, let's say in a rocket engine or a gas turbine engine or whatever it is, you get temperatures that are pretty close to the adiabatic flame temperature, within let's say 100 degrees or something, alright, which is not a lot of deviation when you are looking at something like 2500, right. So we are not talking about a heat loss as a non adiabatic situation. The point we are trying to look for is most of the time when you are looking at the heat that is generated in the combustion, right, we are primarily looking at the hot products that could be used, the heat in the high temperature of the hot products that could be used. Okay. So when you are now looking at something like a steam turbine where you are actually essentially having a high temperature steam that turns the wheels, right, you are counting on the high temperature of the steam to the thermal energy that is associated with the high temperature of the steam to be imported into the turbine blades. Similarly, for the hot combustion products, by virtue of the fact that they have high temperature is what we are trying to utilize. So if you just put a kettle on a stove, okay, what's actually heating the kettle is the hot products. It's not the chemical reactions itself. The chemical reactions are over many millimeters below the kettle. Okay, the flame itself is not really near the kettle at all. Okay, the flame is, if the flame were to happen near the kettle, the flame will get quenched and it will become non-adiabatic. But the flame is actually on the stove, okay, on the burner, and you get these hot products, and the hot products are the ones that are actually flowing around the kettle and heating up the kettle, right. So the question basically then is, what is the heat that you are going to get out of a chemical reaction, or in other words, when you are now looking at these fuels with heats of formation and so on, maybe in lots of practical applications as well as in your high school or wherever you have learned any combustion, you would have come across things like heating value of the fuel, okay, or a calorific value of the fuel and so on. So when I now have a fuel in hand, can you tell me how much heat it's going to give? Okay, don't tell me all these things like the circuitous route over which it's going through, and then heats of formation, transaction, reference elements, and all these things. That's too confusing. Okay, is it possible for me to see the calorific value or the heating value of the fuel from this? Can we? Can we? You can. It's all embedded in here, right. So what we are looking for is, if you now didn't really bother too much, just for the sake of approximate argument, okay, if you didn't bother about the fact that the reactants and the products had different CPs or molecular weights and so on, right. So you're just simply looking at sensible enthalpies, and you're simply saying, I had a bunch of reactants at a, let's say, room temperature or initial temperature T1, okay, and so that means the sensible enthalpy of that was pretty low, and I had to now have this fuel release heat that will increase the sensible enthalpy of what were reactants to start with to a very high sensible enthalpy value for the products. Okay, so the heating value of the fuel is primarily going into changing the sensible enthalpy of what were reactants to what will be products. So essentially that's what is going on. So if you now look at then this part minus this part, that's the sensible enthalpy change that's being effected. Okay, if you now take that to one side, okay, and keep this part and this part to the other side, then it becomes automatically that the difference in the standard heats of formation weighted by the individual stoichiometric coefficients of the products and the reactants is effectively the heating value. Okay, or in other words, the heat that is actually released due to chemical reactions in the combustion primarily comes from a difference of the heats of formation weighted by the amounts by which they are. This is basically what's going on. Okay, and it comes directly from here. Okay, so finally the last point that I want to make here is, this essentially says that all of combustion is all about a transaction between heats of formation and sensible enthalpy. We started out with substances, the reactants, which were low in sensible enthalpy, high in heat of formation. Okay, we now finally get to products which are high in sensible enthalpy and low in heat of formation. So essentially it's like what you started out with, low sensible enthalpy, high heat of formation, gets transformed into the other combination. Okay, this is exactly what's going on in determining this adiabatic flame temperature. Okay, so now let's look at the question that I posed towards the end of last class, which is where is the pressure showing up here, right? It's supposed to be a constant pressure process. Where is the pressure showing up here is really the question, right? So the answer to that is sitting in this Ni double prime, or the pressure is possibly the one that's going to dictate what should be the composition of the products is what we expect. Okay, the question is how. Okay, so the next point that we have to look at is composition products. We'll start with a very simple example which is going to be puzzling to us in a minute, right? So example, let's suppose that we consider a reaction where you have CH4 plus O2 gives CO2 plus H2O. Okay, can we figure out, first of all, how many species are there in this system? 4 species. The capital N here is 4, right? How many, well, I shouldn't ask the next question now. So can we now figure out, let us suppose that we had 1 mole of methane, okay, and then we'll do what's called as balancing the reaction, right? So we now have 1 carbon atom here, 1 carbon atom here, that's fine, and then we have like 4 hydrogen atoms here, we have only 2, so we get 2 moles of water there, and then we have like 2 oxygen atoms here, and then 2 there, we have only 2, so we have this. This is supposed to be a stoichiometric reaction. Yeah, so this is what we expect. Now here it is pretty clear. The composition of the products is just as clear as the composition of the reactants. Okay, this is the stoichiometric right? So so CH4 plus O2 will be fuel rich, because we are starving the system of 1 mole of oxygen, and CH4 plus, let us say 3 O2 is fuel lean, right? And correspondingly we should now be able to put in, let us suppose that some excess in the case of fuel rich, we now suspect that there must be some excess amount of methane that is remaining as products, and in the case of fuel lean there is like some excess amount of oxygen that's remaining the products. We should be able to find out. Yeah, so for example, we now have CH4 plus 3 O2, whereas 1 mole of CH4 is going to consume only 2 moles of oxygen. There will be 1 mole that is excess. Okay, and if there is 1 mole that is excess, what's going to happen to the adiabatic flame temperature? Why would the adiabatic flame temperature decrease if you now had a excess amount of reactant that is off stoichiometric condition? The answer is you are now actually soaking up so much amount of sensible enthalpy for the excess reactant that is remaining for it to be also taken to the adiabatic flame temperature. You see, therefore you are not going to reach a very high adiabatic flame temperature. It's sort of like you now have this excess reactant that is remaining there, which wants to share the pie on what is available for the sensible enthalpy rise. Okay, so you are not going to rise a lot, whereas if you didn't have any excess, okay, it's only these products, the stoichiometric products that are remaining, then they are the only ones that are going to actually go high up in the sensible enthalpy. Therefore they can actually reach fairly high temperature. So what it means basically is near the stoichiometric condition, I am not saying at, okay, and let me qualify that a little bit, near the stoichiometric condition is where we can expect to have the highest adiabatic flame temperature. Okay, off stoichiometric conditions the adiabatic flame temperature drops, because you are having excess of one of those reactants that also needs to be heated up to the adiabatic flame temperature, therefore you do not get up to that high an adiabatic flame temperature as you would without the excess reactant, right. Okay. So why near instead of at? It's got to do with how you look at the sensible enthalpy. Recall that we could look at the sensible enthalpy as an integral Cp dt, or if you are thinking calorifically perfect gas, which is simpler, it is like simply Cp times T adiabatic minus T difference, right. So it now matters on what is the Cp of your reactant, okay. So typically you will have, and the Cp will depend on the molecular weight, okay, and typically we expect that the fuels will have lighter molecular weight when compared to oxidizer, and therefore a higher Cp, and so if it can actually hold more heat, it is going to decrease the temperature, because the Cp is now holding the heat and not allowing for the temperature to rise, okay. So that is going to, so if you are now looking at how the adiabatic flame temperature is going to vary as a function of fuel air ratio, okay, you are going to actually have a peak that is slightly away from the stoichiometric value, because the Cp's of fuel and oxidizer and the reactants, they will be different. So you have to work that out, okay. The other thing that you can also think about is, in this reaction we are only looking at O2, but in reality it could be air, which means you have a lot of nitrogen involved, right. So you now have nitrogen which does not participate in the reactions, that means it shows up on either side of this reaction, okay. What is the consequence of the presence of nitrogen for the adiabatic flame temperature relative to if you did not have the nitrogen? Obviously you are going to have much less adiabatic flame temperature, because the nitrogen is now sitting there soaking up the heat, okay. So it is now going to contribute to the sensible enthalpy component as well. So when you now have a total amount of sensible enthalpy that is available for you to increase the temperature, the nitrogen also comes in for its share, therefore you do not get to a very high sensible enthalpy. Keep in mind the nitrogen has a Cp which corresponds to a diatomic molecule, okay. So instead of nitrogen, if you had, let us say, argon, alright, which is a monatomic molecule, its Cp is different, because Cp typically depends for gases particularly on the atomicity of the molecule, okay, monatomic, diatomic, polyatomic and so on, okay. When it is polyatomic, whether it is linear or is it non-linear and so on, right. So it depends on whether you have rotational degrees of freedom that needs to be considered and all those things, right. So if you now replace the nitrogen by argon, then you will now find that the way the diluent, so effectively nitrogen as well as argon was acting like a diluent, and the diluent is now going to the monoatomic nature or the diatomic nature of the diluent is going to change the way that the adiabatic flame temperature comes down. And even within a monatomic, if you now try to replace argon by helium, yeah, so argon has a higher molecular weight, helium has a lower molecular weight, correspondingly the Cp changes, right. So on a per unit mass basis, and then if you now calculate things on a per unit mass basis, then you will again see differences. So I would like you to work out those kinds of details, like for example in an exam we can directly ask you, if I now replace so much amount of nitrogen by so much amount of argon, what is going to happen to the adiabatic flame temperature, increase or decrease, okay. So you should be able to figure that out, okay. So those are things that we can look at. What we were talking about is the composition of the products, and as I was pointing out, if you have a stoichiometric mixture where you have considered these two as the stable products finally, you now know exactly what the composition is. If you are now looking at off stoichiometric situation, you could still expect one of the reactants to be in excess and find out what it is or how much it is excess, right, in which case you still know what the composition of the final products are, including the excess reactant that was on the product side, okay. So where is the problem? We could find out the composition of the products, we know what the Ni double prime is, the pressure didn't come into picture at all. Is there a problem? or doesn't the adiabatic flame temperature not depend on the pressure at all, right? Because you might expect, because it's based on enthalpies, and for ideal gases we showed that enthalpy is only a function of temperature, it's just a balance of enthalpies. Okay, constant pressure, yeah, we are balancing enthalpies, therefore constant pressure, otherwise it doesn't matter. So pressure doesn't come into picture at all. That's not quite true. Okay, in reality, now we have to look at reality. Okay, in reality these are not the only products that happen. These are the products that we would like to keep. Okay, these are the products that we would be expecting as the stable products. But imagine when you now have these as the final stable products, and keep in mind that these are the final stable products, that means they have the highest negative heats of formation, which is now going to give rise to an estimate of a very high adiabatic flame temperature. That is to say, if in case they were the only ones to exist, you are now going to have a high enough adiabatic flame temperature that is now that's now going to cause a decomposition of these, right? They just can't exist at those temperatures the way they are. Okay, so H2O could now get decomposed into OH and H, for example, right? And that decomposition is going to soak up some energy and decrease the adiabatic flame temperature. That's one problem as far as the T adiabatic is concerned. But the other big problem that we are talking about is how much H, how much OH. If I now have to factor in that you need to have some H and OH also thrown in there, okay, how much H and how much OH, because I need to know that, otherwise I wouldn't know. First of all, it increases the number of species, right, total number of species. The second thing is, what is the Ni double prime for those, and if you're not going to bring in those, this is going to change. So pretty much everything changes, right? So how do we bring the existence of those kinds of ions or radicals in there, okay, as decomposition products of the stable products? What we then assume next, okay, is that, let us suppose that you started out with reactants and they gave, so that you could go through this fictitious path and all that stuff that we talked about. You are now looking at the final state. The final state of adiabatic flame temperature is such that these products are in equilibrium with their dissociation products. Okay, so if you now have H2O, okay, it could be in equilibrium with OH and H, right? So if CO2 were to decompose, it could be in equilibrium with its decomposition products. Again, we don't know exactly what would be the nature of those decomposition reactions, right? There could be multiple ways by which these decomposition reactions could happen. So the simplest way again is for us to hypothetically assume formation equilibria. That means if you now look at many more species of these many more unstable species to be considered, right? We now have to actually consider their formation reactions as the equilibrium reactions. Okay, so let's just go through that a little bit more. So in reality, we just don't have only the most stable products, but many unstable products of dissociation, right, as well. Okay, so in general, we could assume, say for the H2O2 reaction, right, H2O2 reaction, if you now say H2 plus half O2, we have strictly speaking, if I were to look at only the stable, most stable product here, it has to be H2O. Okay, so what I would actually have to say is I have only, and I would like to say it's only 1 mole, so that means I know A is equal to 1, yeah, but in reality we have to now consider BOH plus CO2 plus DH2 plus EO plus FH. Alright. Now what happens here is, because this is stoichiometric, okay, we weren't expecting either O2 or H2. Okay, if it were off stoichiometric, let's say if it is fuel lean, right, you could expect some O2. If it is fuel rich, we could expect some H2. That's what we were thinking before. But now what's happening is, you could have H2O decompose into OH and H, but H could combine to form H2. Okay, and you could also have O atoms come up, okay, during this decomposition, which can recombine to form O2. So you now have a soup bowl of lots of things that we didn't really bargain for. Alright, and all these things are there. So how do you handle them? Okay, so effectively we now need to have 1, 2, 3, 4, 5, 6 unknowns that we need to work out. Okay, so previously how many unknowns did we actually work out by balancing the reactions? We worked out about 2 or 3. Okay, 2 here, if one of them were excess we would just be able to handle that as well. How did we do that? How did we actually end up finding out the composition of the products? By what's called as balancing. Okay, what were we doing when we were balancing? We were actually looking at counting at the number of atoms of a particular type. Okay, so what did I do? I said I have 1 carbon atom here, I have 1 carbon atom here, through 4 hydrogen atoms here, but only 2, therefore I put a 2 there, and so on, right? So I was essentially looking at a particular atom type and I was balancing the number of atoms. This is the hallmark of chemical reactions, because chemical reactions are all about exchanges only at the electron level and not at the nuclei level. Okay, and what you are looking for is a mass balance in a chemical reaction. Mass is conserved, it is the nuclei mass that we are looking at. Okay, so we are actually mentally writing what's called as atom conservation equations for each atom. And you can only write as many atom conservation equations as the number of atom types that are there in the system. Okay, so in the case of, so to give you an example, so in the case of CH4 plus O2, how many atom types are there? 3. Okay, we have carbon, hydrogen, oxygen. So we know we can call this a C-H-O system. Okay, CHO system. Okay. In the case of the H2O2 system, how many atom types are there? Only 2. Okay, so if you now were to write atom conservation equations for these, okay, in an attempt to balance the reaction, we would get two equations, but we still are actually having 6 unknowns. That means there are 4 more unknowns for which we need to develop equations, right? So let's first do what we can, which is atom conservation. Atom conservation equations, which is on the left hand side for H atoms we can write 2, that's given to us. Okay, so 2 is equal to, we have 2A plus B plus 2D plus F, basically looking at wherever hydrogen shows up. Okay, and for O atoms we have 1 equal to A plus B plus 2C plus E. Okay. I want to note here that we could have also considered O3 ozone, yeah, H2O2, and there is this notorious unstable species called HO2, okay, but they are too unstable, okay. If we were to consider them, that means we will have 9 species, okay, and then we are still stuck with only 2 atom conservation equations. That means we now have to develop 7 more equations, right, and what we expect to find is these will be in very trace quantities. That means if you now had after H, if you had G, H and I, for these G, H and I values will be very small, is what we are expecting, okay. Therefore we are neglecting this. So what's happening now is the final answer for the adiabatic flame temperature actually depends on how many products you are willing to consider. If you were to consider only 2 products, you will have a fairly high estimate of the T adiabatic, okay. If you want to have realistic estimates, that means you have to consider more products. How many more depends on how cumbersome you want to get yourself into, right. So we want to be reasonable, that means we neglect some most unstable species, but we have to consider some less unstable species also in the picture, okay. So and then we have to now look at equations for these. So what did I say? We now consider hypothetical formation equilibria for the other ones, right. So effectively what basically happens is you now look at OH, O and H for example, and H2O, okay. These are ones that are not reference elements. H2 and O2 are reference elements. So in your mind you should be essentially looking at these 2 equations actually serving the cost of O2 and H2, which are the reference elements for the 2 atom types that we are looking at. That means for every reference element that is there as part of the products, okay, it corresponds to a certain atom, and the atom conservation equation for it is essentially tagged to its coefficient. Is like mental note. It's all of them are coupled together. It's like it's difficult for you to say this equation belongs to that and so on, but for us to number or what do you call enumerate the number of equations that we have, effectively any product that is not a reference element is what we will be writing the hypothetical formation equilibria based on the reference elements, okay. So then you will get the additional equations. So that's what we are going to do now, which is equilibrium formation equilibria reactions, right. So we now say H2 plus half O2 gives and takes H2O, half O2 gives and takes O, half H2 gives and takes H, and half O2 plus half H2 gives and takes OH. So obviously when you write formation equilibria for H2 and O2, it will simply be H2 gives and takes H2. So that's no news, okay, you know, or that's no news and therefore there is no use, okay. So here there is some use to actually considering hypothetical formation equilibria for non-reference element products, okay. That's exactly what we are trying to do here. So with this, what can we write? Okay, we are assuming equilibria, therefore we can write equilibrium reactions, equilibrium equations, okay. So this means for these we can write KPF at T adiabatic. We don't know what is T adiabatic, but we suppose that at this adiabatic flame temperature is where the equilibrium is existing between the hydrogen, oxygen and water, oxygen and its atomic form, hydrogen and its atomic form, and oxygen, hydrogen, and OH, right. So we have to write these at T adiabatic and then try to find out what it is. So pH2O divided by pH2 PO2 to the half Kp Kpf T adiabatic we have to have the subscript here for, let's say, O, then it is PO divided by PO2 to the half Kph Kpfh T adiabatic equals pH divided by pH2 to the half and Kpfh2 I'm sorry OH equal to POH divided by PO2 to the half pH2 to the half, right. Now we didn't bargain for the pressure to come in, the partial pressures, these are partial pressures, right. We didn't bargain for the partial pressures to come in there, so we want to now change these partial pressures to the actual pressure, the total pressure. When I say total pressure, it's not like the stagnation pressure in gas dynamics, this is the total sum of all the partial pressures, okay. This is the thermodynamic pressure, okay. So now we are beginning to talk about the effective pressure. You see, the pressure at which the entire reaction from the reactants onto the products is happening is basically going to influence the proportion of the stable products versus the unstable ones, okay. So dependent upon the pressure and dependent upon the Kp equations, the proportions of these are going to get altered, okay. Therefore the pressure is going to influence the existence and the amount of the unstable reactants that will soak up some heat and alter the adiabatic flame temperature of the products. You see, that is how the pressure is essentially coming into picture. So here we can write Pk equals xk times P, where xk equal to nk double prime divided by n, where n equal to sigma sigma over all k nk double prime. That means you add up all the number of moles of all the products together, which we don't know yet, okay. This is what we are trying to find out. We are trying to find out the nk double prime, yeah, but whatever it is, it's going to have a total, and the total will be n, and then if you now take the value of n, the kth species double prime divided by the total, you get xk, and xk times P. So the P is the pressure at which the reaction is happening, right. There is a pressure at which the reaction is happening. Then we are beginning to get the P in the picture, and therefore you can now plug this in here and all these things. So effectively you are now going to get, well, in our case, or for example, if you now assigned numbers for k going from 1 to n, let's suppose that 1 corresponds to hydrogen, 2 corresponds to oxygen, 3 corresponds to water, and so on, then A would be n3 double prime, okay. So in this thing we would now plug in n3 double prime, n4 double prime, and so on, okay. So effectively everything is going to be in terms of some nk double prime, all these things you can now rearrange them, okay. So how do you do this? So in general we could have any stoichiometry, right, given by let's say half NH H2 plus half NO O2 gives, we now have to write NH2O H2O plus N H2 H2 plus N O2 O2 plus N H H plus NO O plus NOH OH. Okay, so I just don't want to use ABC etc. anymore, because I might just cross 26. Okay, that's so many alphabet, so many letters of the English alphabet. So I'll just keep N subscript whatever it is, and then we get 2 NH2O plus NOH plus 2 NH2 plus NH equals capital NO. Capital NO essentially refers to the number of oxygen atoms in the entire system. Okay, we took a half NO because we have an oxygen molecule. Okay, and NH2O plus NOH plus 2 NO2 plus NO equals NH, which is the, I'm sorry, I made a mistake. This is NH over there and NO over here. These are the atom conservation equations. Okay, N equals NH2O plus NH2 plus NO2 plus NH plus NO plus NOH. Okay, and Kp, let's say Kp1 equal to NO divided by NO2 to the half, P divided by N to the half. You now plug in these mole fraction information, okay, in terms of pressure and N. So strictly speaking, actually we can get rid of this and then say this is H2O, and no, I'm sorry, this is KPO, or specifically we should say KPFO. This is KPF H equal to NH divided by NH2 to the half, P divided by N to the half, and KPFOH equal to NOH divided by NO2 to the half, NH2 to the half, and the P gets cancelled here, so it doesn't show up, and then KPFH2O equal to NH2O divided by NO2 to the half NH2, and here pressure shows up with a negative exponent minus half. All right, from this we will now do this rewriting in the next class. So effectively what we want to do is write each of these NO, NH, NOH and NH2O in terms of NO2, NH2, because the denominators are all in terms of NO2 and NH2. Okay, and then we can plug that back in here, and you will now get two equations and two unknowns, okay, in NH2 and NO2. Okay, but those equations are going to look very ugly, and then you have to solve that iteratively and then get the compositions. Once you get the composition, you can go back and solve for the adiabatic flame temperature using this equation. Okay, so we'll continue from here tomorrow.